All right, we're going to look at some problems now from section 8.4, focusing on an infinite geometric series. So remember, a series is adding up the terms in a sequence. For an arithmetic, we're always talking about a finite geometric or arithmetic series rather, meaning that we have a finite number of terms. And when we first looked at geometric, we were looking at the finite as well. But we know there are certain scenarios where we can have an infinite geometric series. And for that to happen, the R, our common ratio, needs to be somewhere between -1 and 1, not including 0. And what that would mean is that when we're multiplying to get the next term in the sequence, each number would be getting closer and closer to 0. And so when you get to the millionth and billionth term, that number is so small that is negligible effect on the actual sum. So remember, our sum formula is the first term over 1 minus the common ratio. So we need to identify those two and use our calculators to help us out with our actual sum. So here, our first term, A1, would be 4 times 0.2 to the 1 minus 1. Well, that's 0, or I'm sorry, 1, because anything to the 0 is 1. So the first term is 4. And there is our common ratio. So R is 0.2. So our sum would be 4 over 1 minus 0.2, or 4 divided by 0.8. And so again, we'll go to our calculators. 4 divided by 0.8, and we see that is 5. Okay, next, so now we're given this series, and we can see by the dots that it goes on and on forever, so that's infinite. So we need to figure out what is that common ratio, because that's not given to us. So you may see it pretty quickly. It's actually one of those things I would say it's a little bit easier here with the fractions. Because I can see that 2 times 8 is 16 and 3 times 9 is 3. Another way to look at it is -6 times our common ratio would equal -4, right? That's how we get the next term. If we divide it by -6, there again, you see R is 2/3. Here's our first term, -6. So our sum is -6 over 1 minus 2/3. -6 over 1/3, and that should be -18, but we'll confirm, divided by 1 divided by 3, there we go, or -18 actually because of the negative. So there's our sum. Okay, again, next we're looking at this, and we have to find our common ratio. So 2 times R equals -5, divide by 2. R is -5. I see that works here as well. But unfortunately, that R is less than -1. So therefore, there is no infinite geometric series because this sum would not converge onto one number. So there is no sum to compute here. All right. One other question that's related to that is how do we turn a repeating decimal into a fraction? And one of the things that we saw in class, and I'll show you again, is that this repeating decimal is an infinite geometric series. So I can write this as 1 plus 0.72 plus, now I can go 0.0072, right? If I combine those, I would have up to that point, plus now 4 zeros, 72, and because of the bar over the 72, that repeats itself. So we could continue this. And so starting with 0.72, this is a infinite geometric series, with our first term A1 being 0.72. And again, we can find our R by taking 0.72 times R would equal 0.0072, right? And you may be able to do this in your head, and I think if you do enough of these, you'll see that. But we have our 0.0072 divided by 0.72, and we get our 0.01. And you can see that each time we're moving the decimal point over 2 more places, and so that's another way to know that your R is 0.01. Okay, so our sum, we still have the 1, so 1 plus, and now we have the 0.01 divided by, whoops, not 0.01, our first term, sorry, it's A1 still divided by the 1 minus R, so 0.72, 1 minus 0.01, 1 plus 0.72, well, that's 0.99, and we can simplify that a little bit. 1 plus, move the decimal point over twice, so now we're going to change the 1 to a common denominator, so we have 99 over 99 plus 72 over 99, and that is going to give us 171 over 99. And so if I go back to my graphing calculator, just to confirm 171 divided by 99, there's the 1.7272 that we started with repeating. So again, a repeating decimal, and a number with a repeating decimal can be written as an improper or proper fraction, and we can use our infinite geometric series to do that. Hope that helps, and we'll see you soon.